Ever wondered how a roundabout keeps traffic flowing smoothly? Your computer uses a similar system for managing tasks, thanks to circular queues. Circular queues are like a well-designed roundabout, ensuring that tasks cycle through efficiently. Just as a roundabout prevents traffic jams by continuously circulating vehicles, circular queues keep your computer's tasks organized and prevent delays. Welcome back to session 10. Today we'll explore circular queues which enhance efficiency by managing tasks in a continuous loop. Additionally, we'll dive into priority queues which reorder tasks based on their importance. When studying any data structure, there are a few important points we need to discuss. First, what is the concept behind this data structure? Next, what are the operations we can perform? And how do we implement those operations? We also need to consider how much time it would take to perform these operations. Finally, what are some practical applications for these specific data structures? In this session, we will discuss all of this for circular queues and priority queues, along with a comparison between different types of queues. For a typical user, whether it's a regular queue, circular queue, or priority queue, what matters most are the operations they can perform. Enqueue adds an element to the end. Dequeue removes the front element. Front retrieves the front element without removing it, and is empty checks if the queue is empty. Essentially, all these queues are examples of an abstract data type or ADT, where the focus is on what operations can be done, not on how they are implemented. But if you're a programmer, the story changes. It's not just about knowing what operations can be performed, you need to know how to implement them. That's where data structures come into play. They handle the storage and management of data for these operations. Just like we used an array to implement a regular queue in the last video, we'll use an array again. In this video, to explore how Enqueue and Dequeue are implemented in memory. Let's dive in. Circular queue is a clever twist on the regular queue. In a regular queue, once you reach the end of the array, you can't go any further. Those first positions become useless until the queue is completely emptied. But in a circular queue, as soon as the rear of the queue reaches the end, it wraps around to the beginning, efficiently reusing space. When we define a queue using an array, memory gets allocated for it. When we enqueue an element, the rear value increases by 1. If we delete some elements from front and the rear reaches the end of the array, it wraps around to the beginning, making use of the available space provided there is any. In this case, the rear becomes 0 again. We simply find the correct index and insert the value. This process is very efficient, taking constant time or big O of 1, because all we're doing is updating the rear value to either increase or reset, then placing the new element in the correct spot. On the other side, we have the dequeue operation, which removes elements from the front of the queue. Similar to Enqueue, the front pointer advances by 1 with each operation. If it reaches the end of the array, it wraps around to the beginning just like the rear. This process is also swift, taking constant time big O of 1, because we are simply updating the front value, either moving it forward or resetting it, to remove an element efficiently. So where do we see circular queues in action? A great example is how an operating system manages tasks. Imagine your computer is running several programs at once. To make sure each program gets a fair amount of processing time, the system assigns a small, fixed time slice to each one in a repeating cycle. Once a program's time is up, it goes to the end of the line and the next program gets its turn. This system relies on the efficiency of circular queues to handle tasks without delays or wasting memory. By cycling through the tasks in a circular fashion, it ensures all programs get processed fairly and efficiently. Regular queues and circular queues work on the FIFO principle and suit best when tasks are of similar priority. However, there are situations where we need to manage tasks based on urgency rather than their order of arrival. This is where a priority queue shines. It arranges elements based on priority, ensuring that critical tasks are processed before less urgent ones. There's no universal way to visually represent a priority queue, we simply choose a method that best fits our needs. There are many ways to implement priority queue. In our implementation, we use two separate arrays, one for storing the tasks and another for storing their priorities. When a new element is inserted, the queue reorganizes itself to maintain the priority order. This rearrangement is reflected in the array with higher priority tasks moving forward. The highest priority task is placed at the front in index 0. If two tasks have the same priority, the one added later is placed after the existing one, following if FIFO for tasks of equal priority. But removing the highest priority task is swift, as the front point to the next element in the array. This takes big O of 1 time since it's always at the front. There are more efficient ways to organize the priority queue, such as using a heap, which we'll discuss when we cover trees. In real-time systems, tasks are prioritized based on importance and urgency. For example, when a phone call comes in, everything else on the mobile halts, such as the YouTube video you are watching at that moment. Today we've uncovered the advanced queue structures, circular and priority queues. These structures not only optimize space and performance but also play critical roles in managing tasks and processes efficiently. Reflect on how circular queues and priority queues impact various systems in your daily life. From managing tasks on your computer to prioritizing critical operations in real-time systems, these concepts are pivotal in enhancing system performance. As you continue your exploration of data structures, consider how linked lists might offer additional insights into dynamic data management and complement the queue structures you've learned about. Think about how understanding these fundamental structures can influence your approach to solving more complex problems in computer science and beyond. Thank you for joining us today. Stay curious and keep exploring. Happy coding!